Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss experimental illustration of uncertainty principle. Two illustration. One is experiments of gamma ray microscope. Another one is diffraction of a beam of electrons by a single slit. Let's begin. Heisenberg's uncertainty principle say that we can't measure position and momentum of a particular particle simultaneously. So, there is uncertainty in position into uncertainty in momentum always greater than equal to s cut divided by 2. Such Heisenberg's uncertainty principle can experimentally verified. Here we discuss two such type of verification. One is experiments of gamma ray microscope. To measure the position and momentum of an electron, a high powered gamma ray microscope is used. This is a figure of a high power gamma ray microscope. This is the electron, we call it as particle, which is at rest at position O, and a gamma ray is incident. Gamma ray, that is high energy, means E is equal to s nu. The frequency of such type of gamma ray is high. High frequency means lower in that of wavelength. According to that de Broglie hypothesis, the wave associated to that of gamma ray, we call it as a photon of gamma ray. That incident photon having the momentum s divided by lambda dash. Lambda dash be the wavelength associated to that of gamma ray of photon. When that gamma ray is incident on that of electron, so that the photon is scattered and that electron is recoil. We studied in the phenomenon of Compton effect, and that scattered photon have increase in wavelength. The recoil electron is not necessary in that section, so we avoid that one. And a high power gamma ray microscope is used to detect what be the position of such electron. So, the resolving power of such microscope is given by del x is equal to lambda divided by 2 sin theta. Look that expression. What is resolving power? Resolving power is the minimum distance between 2 points that can be resolved. If we try to resolve the distinction between 2 points, so the resolving power is the minimum distance between the 2 points which can be resolved by that particular microscope. That is the resolving power. Resolve the distinction between 2 points, that is the minimum distance. So, the resolving power of such microscope is del x is equal to lambda divided by 2 sin theta. Again, what is that del x? That del x we call uncertainty in measurement of position of electron. Why? How we see that electron? We see that electron when that scattered photon in between this range from A to B, that range within that of angle plus theta to minus theta. If the scattered photon within that range, so we can easily see that electron. So the position of electron we seen in between these 2 points. So that is again the uncertainty in the measurement of position of electron. So the resolving power, that is del x, which is called the uncertainty in the measurement of position of electron. Next, lambda, that is the wavelength of light. Here scattered wavelength, which is the wavelength lambda, and that of scattered photon with the momentum s by lambda according to de Broglie hypothesis. And theta, that is the semi vertical angle of cone of light entering the objective of microscope, the theta. Let us come to our analysis. We have to showcase the Heisenberg's uncertainty principle, means the product of uncertainty in position and uncertainty in minimum is greater than equal to h squared by 2. This is the uncertainty in position of that of electron, del x, which is lambda divided by 2 sin theta. Now we have to calculate what will be the uncertainty in momentum. Let a gamma ray of a photon of wavelength lambda dash, this is the momentum s by lambda dash, is incident upon that of electron. The photon collide with that of electron and scatters. This is the scattering of that electron. Scatter into the microscope with increase in wavelength, that the wavelength of scattered photon is increased, that we study in case of Compton effect. And the scattered photon enters to that of microscope anywhere between OA and OB. In between this region, the scattered photons are entered, that is within that of angle range plus theta to minus theta respectively. OA treated as plus theta, OB treated as minus theta. So what will be the uncertainty in momentum of that of electron? Look here, that is the momentum of scattered photon along OA. This is the angle theta. When we resolve that momentum vector, one is along x direction, another is along y direction. So along y direction, that component is s by lambda cos theta, and along x direction, that component is s by lambda sin theta. Our requirement is along x direction. So first we showcase it due to that plus theta, what will be that momentum along x direction, and again due to that minus theta, what will be the momentum along x direction, and finally the uncertainty in that of momentum. Therefore, the uncertainty in momentum of electron along y direction, along x direction, is equal to, first the uncertainty of momentum due to plus theta. This is or we can say this is the loss of photon, the loss of photon loss of momentum of photon, loss of momentum of photon imparted to the electron along x axis due to OA, due to along OB. OB minus same the loss of momentum of photon, the loss of momentum of photon imparted to the electron along x axis due to along OA. So, the uncertainty of electron along x axis, that is represented as del px. So, what will be the loss of momentum of photon imparted to the electron along x axis due to along OB, due to along OB, that is OB due to that minus of theta. Here is the incident photon S by lambda dash, S by lambda dash is the incident photon. The x component of such momentum, here S by lambda theta, so that component is S by lambda cos theta, and this component S by lambda sin theta against this direction. So, S by lambda sin of minus theta, that is minus sin theta. That is minus S by lambda sin theta. Minus, understand it? That is the loss of momentum of photon imparted to that of electron along x axis due to OB. What is the uncertainty of momentum in that of x axis? That is uncertainty in that region due to plus theta, due to minus theta. What will be the uncertainty of momentum along x axis due to OA and OB within that of range plus theta to minus theta? First, along OB, this is the incident photon along x axis, that is S by lambda dash. That component along x axis minus S by lambda sin theta, since it is against that of incident photon. Next, the loss of momentum of photon imparted to the electron along x-axis due to OA, here that is h by lambda dash minus that momentum is resolved, this component h by lambda cos theta, that component h by lambda sin theta, which is the same direction of that of incident photon. So the resultant h by lambda cos theta, it can be solved h by lambda dash plus h by lambda sin theta minus h by lambda dash plus h by lambda cos theta. Sorry, that is h by lambda sin theta, this component cos theta, that component sin theta. Sin theta, here is sin theta. Cancelled out, it is 2h by lambda sin theta. Equation number 2. This is from equation number 1, that is from equation number 2. This is the uncertainty in position, that is the uncertainty in momentum. Therefore, multiplying equation 1 and 2, therefore multiplying equation 1 and 2, we get del x into del px, uncertainty in position into uncertainty in momentum. Uncertainty in position, lambda divided by 2 sin theta into uncertainty in momentum, 2 h by lambda sin theta. H cancelled out, sin theta cancelled out, 2 cancelled out, lambda cancelled out, 1 only h is there. So del x del px is equal to h, that equation number 3. But if we consider a large number of waves, in case of a group consisting of a large number of waves of continuously varying frequencies, the product of uncertainties, in position and momentum is given by, that equation is written as del x del px greater than equal to h by 4 pi, or simply del x del px greater than equal to h cut by 2, whereas h cut is equal to h by 2 pi. This is nothing but Heisenberg's uncertainty principle. Thus, the experiment shows validity of Heisenberg's uncertainty principle. from that of gamma ray microscope, we detect the uncertainty in position and momentum of electron, and finally it validates Heisenberg's uncertainty principle. Another illustration, diffraction of a beam of electrons by a single slit. This is a single slit and electrons beams are incident through that, and the diffraction pattern we see in that of screen, and the diffraction pattern, that is the central maxima, then minimas, this is the first minima, second minima, like this diffraction pattern we see, delta y, whereas width of that of slit, from that of phone of a diffraction at a single slit. So, the equation is d sin theta is equal to n lambda, whereas d stands for width, as we taking it along y direction. So, for that purpose we use delta y. In that of case, d is equal to delta y. For first minima, n is equal to 1. So, that expression changed as delta y is equal to n lambda by sin theta. That electrons within that of single slit. So, what be the exact position we can refer. So, that is the uncertainty in position of such electrons. Since the electron beam producing diffraction pattern can pass through any point through that of slit. So, this is the uncertainty in position of electron, and which is given by delta y. Delta y is equal to n lambda by sin theta, that is the uncertainty in position of such electron. Then we calculate what will be the uncertainty of momentum of such electron. First, electrons travel along x direction. When it pass through that of slit and form a diffraction pattern on the screen, so the deviate, and that deviation along y direction, and that uncertainty in that momentum within plus theta to minus theta. So, if we resoluate that momentum along y direction, in x direction, that is p cos theta, along y direction, that is p sin theta. Similarly, here minus of theta, that is along x direction, p cos theta, along y direction, p sin of minus theta, which is equal to minus p sin theta. Initially, the electron beam is moving x axis, hence it has no component along y axis. At the slit, it deviates from the original path to form diffraction pattern on the screen, hence it has momentum component along y axis, as we show in that of figure. This is the momentum component along y axis, and the electron is anywhere in that of diffraction pattern from that of angle minus theta to plus theta along y axis. That will be the uncertainty in momentum of such electron along y axis. So, uncertainty in momentum of electron along y axis is equal to p sin theta minus of minus p sin theta, which is given by del py, or del py is equal to 2p sin theta, that equation number 2. Therefore, del px, position del y, momentum del py, n lambda divided by sin theta into 2p sin theta, sin theta cancel out, delta y delta py is equal to 2p n lambda into 2p. From that of de Broglie hypothesis, so that p is equal to h by lambda, p is equal to h by lambda from de Broglie hypothesis. So lambda cancel out, two where is the n term? That is not n term. Here n is equal to 1 is putted. No n term is there. This is 2h as you replace it, del y del py which is greater than equal to h cut divided by 2. As we know, h cut is equal to h by 2 pi, which is equal to 2h, or which is greater than equal to h cut by 2. Which is the verification of Heisenberg's uncertainty principle. Verification of uncertainty principle by the diffraction of beam of electrons by a slit. So here with the help of this video lecture we understand the experimental illustration of uncertainty principle, experiments of gamma ray microscope. It's verified. Next, diffraction of a beam of electrons by slit, and finally it is verified. So with this useful and informative notes, let me wind up the session. Thank you.